Hello everyone, this is Team 13, and our topic is CSS injection, a study of secret exfiltration and UI spoofing. My name is Ruijie Zhang, and there's my teammate Theodoros. We're going to talk about two different applications of CSS injection. The first one is CSS injection for secret exfiltration, and the second one is relative path override for UI spoofing. For a quick recap, CSS injection can be used for secret exfiltration where the attacker injects style sheets into the victim site, causing it to trigger secret exfiltration requests to the attacker server. So for the threat model, we define the attacker to be a passive web attacker whose goal is to steal sensitive information from the victim site. As for the victim side, we assume it to have some sort of mitigations against cross-site scripting by disabling all inline scripts and only execute scripts from self. So the first type of attack we're going to talk about is vanilla CSS injection. It consists of the interactions between four entities. The first one, the user, is the one that's going to browse exploit site. Second one, the exploit site, controlled by the attacker, will be framing victim site and colluding with the attacker server. Third, the attacker server, also controlled by the attacker, is responsible for the generation of malicious style sheets and the reconstruction of the secret. Lastly, the victim site is assumed to contain confidential information that the attacker is trying to steal. So here is the attack scenario for vanilla CSS injection. It starts by the user visiting the exploit site, which frames the victim site. The victim site will be requesting style sheet from the attacker server, and after evaluating the style sheet, it will trigger secret exfiltration request to the attacker server, causing the secret to be exploited. So basically, this loop will have to be repeated until the entire secret is exploited. And the second type of secret exfiltration attack is import tag injection. It utilizes the fact that import tags will be evaluated sequentially on some browsers. So now only one injection is needed to exfiltrate the complete secret, and it does not require framing. So let's say if there is a style tag with 3 import tags in it. What the browser will do is that it will trigger 3 import requests to attacker.com. And instead of waiting all 3 style sheets to be fetched, the browser will start evaluating the style sheet as soon as one of it is returned from attacker.com. So basically it comes as a first come, first served characteristic. Here's the attack scenario for import tag injection. So now the exploit site is not needed, and all interactions are between victim site and the attacker server. So you can see it relies on the multiple import requests, and the attacker server will try to exploit the entire secret by responding to these import requests sequentially until the entire secret is exfiltrated. So here are some mitigations and limitations for these two types of attacks. For vanilla CSS injection, since it relies on iframing the victim site, it can be mitigated by disabling iframe. And for both vanilla CSS injection and import tag injections, since they both rely on background image load, they can both be mitigated by restricting the allowed image source with CSP. Here are the results by testing these two attacks on Safari, Firefox, and Chrome. So for vanilla CSS injection, it works on all 3 browsers as long as they do not have iframe disabled or image source restricted. On the other hand, for import tag injections, it only works on Chrome since it is the only browser that supports sequential evaluation of the style sheet in real time. However, even for Chrome, it can still be mitigated by restricting image source with CSP, since import tag injection also relies on background image load to trigger the secret exfiltration request. So that's all for secret exfiltration. Now Theodoros will talk about relative path override for UI spoofing.
Now we will look at a different class of attacks that is called relative path override and arise from the different interpretation of the URLs between web servers and browsers. RPO vulnerabilities can occur in web pages that reference resources such as style sheets using relative URLs. The browser needs to expand those relative paths to absolute URLs in order to request the relevant resources, something that can lead to an issue often referred to as path confusion. To give more context into this issue, let's assume that we have a vulnerable page hosted in the domain victim.com/home/index.php that reference an external style sheet using a relative path such as style/custom.css. When a GET request to this URL is encountered, the browser will try to interpret the absolute path for the style sheet by assuming that it is part of the parent directory victim.com/home, and the style sheet will be loaded properly. However, if the URL contains a slash in the end, the web server will still return the same document, but to the browser, the URL will appear to designate a directory and the style sheet will be requested from victim.com/home/index.php/style/custom.css. In this case, the server may interpret style/custom.css as a parameter to the script index.php and return the HTML document as a style sheet. Given this attack scenario, we define a web page as exploitable if it references a style sheet using a relative path and the server is configured to serve the page even if the URL is manipulated by appending path separators. In addition, it is important that the page contains at least one injection vulnerability or generally can reflect style directives. The page should not contain a base tag and the injected CSS should be correctly interpreted by the browser in order for the attack to work, which relies on the way the browser treats different document types. In order to demonstrate the feasibility of this attack, we create an exploitable web page called friend.php, which is supposed to depict the attacker's profile on a social application called Facebook. We suppose that the attacker's goal is to leverage the RPO vulnerability and inject CSS directives in order to manipulate the UI of the page and trick the victim into accepting the connection request. The legitimate profile page of the attacker is shown here. The goal of the attacker is basically to revert the colors and description in the two buttons at the bottom. Through another page called changename.php, the attacker can change their profile name in this app, which is stored in the database and reflected in friend.php. Since the input is not sanitized, the attacker can inject CSS directives in the name input field. An example of the payload injected by the attacker is shown here for the green button. Basically, it includes one directive to force the content to be invisible, another one to insert a new description that matches the description cancel of the red button, and the last to change the background color. Since a payload would be represented as the profile name, there are also some directives to change it so that it looks legitimate as before. If we visit the profile page after the injection but using the legitimate URL as shown in the left screenshot, we will notice that the CSS directives are not evaluated and the payload is presented as the profile name. This is because there is no path confusion and the browser fetches a legitimate style sheet. However, if the attacker alerts victims to visit the profile page by clicking on a manipulated URL that contains a slash in the end, the injected CSS executes and spoofs the UI as shown in the right screenshot. Basically, in this case, the problem with path confusion that we discussed before is triggered, and the HTML page references itself as a style sheet. We can verify that the two buttons at the bottom are reverted while the name doesn't reveal the payload but is spoofed and controlled by the attacker. The most obvious mitigation for this attack is to only use absolute URLs when requesting external resources from the HTML document. Another mitigation is to use the base HTML tag, which instructs the browser on how to expand relative path instead of relying on the URL of the page. In both cases, the browser will know which resource to request from the web server. Another strategy is to use the correct document type in the page and more specifically include the directive doc type at the beginning of the page. In this way, we enforce the full standards modes in browsers instead of the quirks modes, and the self-references will not work because the malicious CSS is of type HTML instead of the expected CSS. Lastly, eliminating injection vulnerabilities decreases the attack surface of web pages and injection sinks that can be leveraged by attackers. We tested the implementation in all major browsers and succeeded in all cases. Then we test each mitigation separately, and surprisingly, it seems that all of them are adequate to thwart this attack in all browsers as shown in the table. Here is our timeline with the task we completed each week, and here is the distribution of the work between me and Ray. To sum up, it is important to highlight that CSS, although seemingly benign, can be leveraged for secret exfiltration as well as UI spoofing. CSP and X-frame options can provide strong mitigations against CSS injection, while threat analysis has also the potential to detect injection sinks and could be further researched in the future. From the RPO, we learned that absolute paths, the base tag, and the correct document types can mitigate path confusion, but injection is quite more challenging to mitigate compared to cross-site scripting. That's the end of our presentation. If you have any questions, please feel free to ask. Thank you.